Hello and welcome back. Today is Lecture 2-2 on phasors and impedance. If you're following along with the textbook, you should be reading sections 9.3 through 9.4. The learning objectives for today's lecture include students should be able to perform phasor addition, subtraction, multiplication, and addition, calculate the impedance of resistors, inductors, and capacitors in an AC circuit, transform a circuit with a sinusoidal source into the frequency domain by using phasor representation, and use KVL and KCL to find AC voltages and currents. Let's get started. Example 1. What is the correct phasor polar expression for the effective RMS current in the graph shown with respect to the voltage V of t? The dashed line is I of t, and the solid line is V of t, which is our reference. The first thing you should notice is that the dashed line is a sine wave and the solid line is a cosine wave. So then, using our phasor diagram that we discussed in the previous lecture, we can see that there is a phase difference between the cosine and the sine of 90 degrees. So if I want to write a sine wave as a cosine, then that is the same as writing cosine omega t minus 90 degrees. If we wanted to find the equation of the signal, we note that the period is 4 seconds. So the frequency would be 1 over 4 hertz, or the angular frequency would be 2 pi f, or pi over 2 radians per second. So that sine wave is cosine pi over 2t minus 90 degrees. So what that means is that there is a negative 90 degree phase shift between I of t and V of t. So the next thing I have to do is to find the effective or the RMS current. The effective or RMS current is found by noticing that the amplitude of the current is 50 amperes. So the RMS current would be 50 divided by the square root of 2, which is 35. So this means that the answer to this problem should be 35 with an angle of negative 90 degrees. Example 2. If Z1 is 24.2 with an angle of 32.3 degrees, and Z2 is 16.2 with an angle of 45.8 degrees, what are Z1, Z2, and Z1 divided by Z2 respectively? To multiply complex numbers, we multiply the magnitudes, 24.2 times 16.2, and we add the angles, 32.3 plus 45.8. So that product is 392 with an angle of 78.1 degrees. Next, to divide complex numbers, you divide the magnitudes and subtract the phase angles. So 24.2 divided by 16.2 is 1.49, and 32.3 minus 45.8 is negative 13.5 degrees. So this means that the answer to this problem is letter B. Example 3. The following waveform repeats every 10 milliseconds. What is the average value IDC of the waveform? So the first thing we'll see is that the period t is equal to 10 milliseconds. And then we need to write the formula for the average or the DC value, and it's 1 over the period, the integral over 1 period, I of t dt. Notice that should have been IDC, I average, not V. And integrating a curve is the same as finding the area under the curve. So we can find the area of the first rectangle, the area of the second rectangle, and the area of the third rectangle, add them together, and then divide by the period, and that would be the same as finding the average value. So that would be 1 over 10 milli times the quantity, 2 times 40 is 80 milliampere seconds, minus 2 times 10 is minus 20 milliampere seconds, plus 2 times 30 is 60 milliampere seconds, and we get 1 over 10 milli times 120 milliampere seconds equals 12 amps. So the correct answer is C. So next we're going to find the impedance for a resistor, inductor, and capacitor by looking at how they respond to a sinusoid. So first you'll see that voltage and current are in phase for a resistor, so V equals I times R. And Eli, or voltage, leads the current by 90 degrees for an inductor, and ICE, the current, lags the voltage by 90 degrees for a capacitor. So if you actually plot these values, you'll see that the voltage and current are out of phase. And from that, we're able to determine the impedance of an inductor to be J omega L, which represents that 90-degree phase, or the impedance for the capacitor is 1 over J omega C, which represents that 90-degree phase as well. So now going from the time domain to the frequency domain, we use phasor diagrams to represent these values, where the horizontal axis is the real axis and the vertical axis is the imaginary axis. So if we label the voltage with a phase angle phi, then the current through the resistors would have the same phase angle because they are in phase, but there may be a difference in the vector magnitude, which would represent the difference between the voltage and current as scaled by resistance. So here we see that for an inductor, Eli, voltage leads current, and that the voltage is shifted to the left of the current. So if the current is in quadrant 1 with an angle phi, then the voltage is in quadrant 2 with an angle difference between those vectors of 90 degrees. And notice that the vector would rotate around that axis based upon the frequency omega. Then for ICE, the capacitor, current leads voltage, which means that the voltage is shifted to the right of the current. So if the current is in quadrant 1 with an angle phi, then the voltage is in quadrant 4, and the difference between those vectors is 90 degrees. And the length differential for both of those would be based upon either J omega L for the inductor or J omega C for the capacitor. Ohm's law in the frequency domain is stated as V equals I times Z, where Z represents the impedance of the resistor, inductor, or capacitor. So the voltage across the inductor is J omega Li, the voltage across the capacitor is 1 over J omega C I, and the voltage across the resistor is I times R. So what you see here is that in the frequency domain, the resistor impedance is the only one that's the same as the time domain impedance. In all cases, impedance is measured in ohms, where the real part of the impedance is resistance and the imaginary part of the impedance is called reactance. Z equals R plus JX is measured in ohms. Admittance is the reciprocal of impedance. So admittance Y is equal to 1 over Z, which is equal to G plus JB, where G is the conductance and B is the susceptance, and admittance is measured in either mhos, which is an upside down omega, or S, which is Siemens. So just to summarize, the impedance of a resistor is R, the resistance of a resistor is R, the impedance of an inductor is J omega L, the reactance is omega L, and the impedance of a capacitor is negative J over omega C, and the reactance is negative 1 over omega C. Now let's try example 4. The magnitude of the reactances of a 10 millihenry inductor and a 0.2 microfarad capacitor are equal when the frequency is what? So we're going to equate the magnitude of omega L and the magnitude of -1 over omega c. So omega squared is equal to 1 over LC, and if you put in the values for the inductor and the capacitor, we get that omega squared is equal to 500 meg, which is 500 times 10 to the 6th power. Next, we're going to take the square root of 500 meg in order to find omega. And we're going to get that omega is equal to 22.36 kiloradians per second. To find the frequency in hertz, we divide omega by 2 pi, which yields 3.56 kilohertz. So once again, the answer is letter A, and you have to pay attention to units. Example 5, an inductance of 35 millihenry has a winding resistance of 7.2 ohms that appears in series with the inductance. It is connected across a 240 volt, 60 hertz supply. Determine the impedance and the current draw. So the first thing we will do is draw a diagram of a 35 millihenry inductor in series with a 7.2 ohm resistor, and then we will draw the supply that is 240 volts and 60 hertz. So the impedance of an inductor is J omega L. J times 2 pi times 60 times 0.035 yields the impedance, which is J, 13.19 ohms. So the current I is equal to V over Z, or the voltage, 240 volts with an angle of 0 degrees, divided by the series impedance, which is 7.2 plus J, 13.19, which yields the current 15.97 with an angle of -61 degrees, and the units are amps. Using that answer in the sinusoidal steady state is I of t equals 15.97 cosine 2 pi 60 t minus 61 degrees, and the units are amps. Example 6. A 20 microfarad capacitor is connected in parallel with a 100 ohm resistor, and the combination is placed across the same supply as the previous example. So the first thing we do is we draw a diagram with the 20 microfarad capacitor in parallel with the 100 ohm resistor, and then we add our supply, which is 240 volts at 60 hertz. The impedance of the capacitor is 1 over j omega c, or 1 over j times 2 pi times 60 times 20 micro, which yields an impedance of -j 132 ohms. So the parallel combination of the impedances would be the product over the sum, 100 times -j 132 divided by 100 plus -j 132, which yields 65.54 minus j 48.13 ohms. So the current I is equal to V over Z, which is 240 with an angle of 0 degrees, divided by 65.54 minus J, 4.13. So the current is 3 with an angle of 37 degrees. And this concludes today's lecture on phasors and impedance.